Hey, how's everyone doing? It's Monday morning. It's the last week of summer. Good to see here Sierra and Courtney and Joseph and Michaela and Michael and Evelyn. How's everyone doing? Hi, right there. Hi, good. Michelle's laughing right there. Nolan, good to see you here. I don't know why my speakers sound louder or quieter. I don't know what's going on. What shall we do this morning? It's your call. It's Monday morning. I'm going to get that coffee going. Got all the coffee. Brian, I'm having issue with my GBM function. I've tried installing the CRAN package, but it says unavailable for my version of R. How can I get this? The CRAN package or Carrot? So you're trying to run a gradient boosted model, right? So let's go talk about gradient boosted models right here. Let's do a gradient boosted model. Gradient boosted in 474. So BAS 474, gradient boosted models, GBM models. Okay, let me get the CRAN one right here. There we go. Here we are. Let's go take a look. Vanish, good to see you. Can you show an example of the chi-squared problem will look like on the exam? Yeah, let's talk about some chi-squared. Stat tool 1. Chi-squared examples. Yeah, Michelle, good question right there. We'll start with Reagan's question, 474. Gradient boosted models. Woo! Here we go. Okay, so we're talking about some gradient boosted models. We got so much stuff open up. Let's go ahead and close out all the data. So much data right there. Hey, Aisha, good to see you there. And so with this, so much data. Okay. Here we are. I even got to zoom in a little bit to help my eyes see it. What's the first thing we do when we start making these models here? When we start doing data mining, we start by visualizing our data, by cleaning our data. And before we run the train function, what do we need to do before we run the train function? Before we run the train function, what do we need to set up? What do we need to set up before we run our train function? Which is very important. What do we need to set up before we run our train function? Can I change this? Nah, that's not going to look good. I set the train rows to be 60% of all models are a factor of at least 1.27 are off by a factor of 1. But when I said to they all have a factor decrease, did I miss something? Okay, so wait. Sierra's saying when I set the train rows to be 60% of all the data, the models are off by a factor of 1.27. What it could be. Now, Sierra, try rerunning it because every time you make the train rows, you're going to get different holdout data. So try, like, this is the thing. We only use seeds for replication. So try using different seeds, like see what happens when you rerun it. Because, and if you notice, like sometimes when I redo it, I'll get new RMSEs or I'll get new AUCs. So because the way the train and holdout are selected randomly, you'll get different ones each time. So it's just possible that maybe there was an outlier and with 60-40 split, you're more likely to maybe get an outlier in the holdout that's going to extremely pull off the model. It sounds like maybe you're doing RMSE because an outlier would more drastically impact RMSE. It would very little impact misclassification because that's like a yes, no. It could also impact AUC worse because AUC, you could have something with a very high probability that's actually no, and that'd be way out of order. So it sounds like you're probably doing RMSE. You're probably doing a quantitative Y variable. Is that right, Sierra? If you're doing a quantitative Y variable and then you have something has a very large miss in your holdout, that's what I'm figuring right there. So probably it's just random bad luck and that just happens. And it's like, maybe there's an issue then. So I would take a look at the holdout data and how it's predicting, and you'll probably see something very far off. Does that make sense? Like you'll see like your holdout and your predictions, and then you'll see something way down there or something way up here, something way away from the rest of the data. And so that's pulling away your ability to do well on the holdout. So you might even notice that and say like, well, without this one value, probably the predictions are a little bit better. Maybe, I don't know, or maybe the holdout just doesn't do nearly as good. I sent you my graph on the project. Can you please help me with interpreting those? I understand those, but I'm really confused how to interpret the GLM model. The Discord, yeah, awesome. Thank you, KP, right there. I'll check it out on the Discord. I think I got decently caught up this morning. So we have, if you notice, only five messages right now. So the potential for extra credit for 201 comes with the note cards and our hours, and we're watching Mew points. So best case scenario, that is like, yeah, it's a lot, right? It's a lot, right, Jessica? There's a lot of potential extra credit. So if you've been doing the note cards, if you've been doing watching YouTube, if you've been doing these extra things, you get a good bit of extra credit. So it's a lot of little help in there that kind of keeps you on track with engaging. I want people to, not everyone might get an A. I want everyone to get an A, but I think the potential is mostly there for B's for everybody. That's the way I like to set up my classes, with a lot of extra credit, lots of opportunities. And if you do all the work, that's always my suggestion to everybody, is like, do all the work, turn in every assignment, then you do pretty well. Here, let me remark this right here. We're going to talk about the GBM. Let me remark it. Talk about the GBM. Good to see you here, Meath. Great job on the Kahoot last night. Okay, and how to compare the training model RMSE and the holdout RMSE, and how to check how our model did. Yeah, KP, we're going to talk about that right here. Exam 3 is the tougher one. I don't think it's tougher than Exam 2. I think it's on par with it. It's just different type of material. So when we make these models here, we need to set up our what first. 474, help me out. We need to set up our what first. If we're going to make models after we've cleaned our data, pre-processed our data, validated our data, visualized our data, what are we going to set up next? Now, you have to set this up. Well, you need to set up your, good answer right there. We'll set up a train and a holdout. We do set up a train and a holdout. I spilled some coffee on myself. So we will set up a train and a holdout. Once we've set up a train and a holdout, we need to set up that fit control. Now, a lot of times I've seen mistakes on this. It's very important to know if your fit control, and we added some notes to this. It's very important to know, oh, nice job, Reagan. We'll talk a little bit more on this right here, and then we'll switch. Reagan restarted their session. I was like, you should have, everything should work, because the package is the Caret package, so from the CRAN server. So you need to know if it's categorical or quantitative. If it's quantitative, and this is what Stats 1 boils down to, you're doing regression techniques like QQ, straight enough, no outliers. So you'll be fitting for RMSE. Now, I personally like to use the repeated CV right here, where you put the number of cross-validation folds you're making and the amount of repeats you're doing. So you're going to get a better idea of how your model does with repeated CV. Now, right here, and we could probably use repeated CV down here also. It doesn't hurt. Down here, the most important thing to know is you're either fitting for accuracy for a categorical Y, or you're fitting for AUC, which is also known as ROC, area under, that's area under the ROC curve. So actually ROC is in this acronym. If you read it as area under the ROC curve, receiver operator curve. So preferably I like to fit to AUC, because it's how the percent of time we properly give the yes class a higher probability than the no class. The percent of the time the yes class gets a higher probability than the no class is what AUC is. And if we get 100%, the yeses are all at the top with probabilities, and that's the way I like to do it. So now we need to make sure we set up our fit control the following way. And the fit control is literally going to be how we're checking this and how we're calculating AUCs and RMSEs. So you have to set this up so you can set a fit control like that and bring it over to your document. Now, when you're doing this, and great points right there, people are saying you have to set up a holdout. Let's go ahead and make a data set right here. Let's pull one up from reg class. So library reg class we'd have to do first in order. There's library reg class. We got data survey 10. And let's go to a training set, train rows. And let's sample 1 through the number of rows of survey 10. That's just a vector of numbers. And then let's say size equals, let's go 60%. Sierra was going 60%. And then the number of rows. So that's 60% of the rows are going to be sampled in this thing called train rows. That's just a vector of numbers. And then we sample 60% of those numbers, because this is what is 60% of how long the data set is. It's going to round that down. So we get train rows of 419 right there. And then we go into here. We go to survey 10. We go to the row space. We select those rows. And then we're just going to do the same thing for the holdout. But the holdout is going to be not the train rows, which means we subtract. So the train gets the train rows and the holdout gets not the train rows. Now that we have this right here, we've got, let's pretend we did our cleaning, all that good stuff. We'll worry about normalizing any other variables, but another time. But now we can basically start making models. And GBM is really some of the most powerful stuff right here. Let's go grab method equals and then GBM. Looks like there's no spaces on that. Oh, we should have a GBM in here. There it is, GBM right there. Method equals GBM. Now, the seeds are going to control the randomness. If you have questions, let me know. We're just doing a little 474, then we'll do some 201 here. Look at all those comments. Ugh, we don't want comments right now. And so we're going to make this look nice and pretty right here. And let's fix it up a little bit. Good to see you, Courtney. So you have to know what's going on with each bit of this. We don't have all the components right now. Verbose, it just means the amount of output it puts out. So let's talk about what's being done right here. What does this mean right here? Who can tell me in the chat what that means? What does that mean right there? What does this mean? What does that mean? I actually had my wife code a little bit last night. Model name, yep, we're just storing into that object. This can be anything. This is just what this will be stored into. It's going to be just, you can call it GBM because we're making a gradient boosted model. So that's just what we're storing into. It just says create this thing here. It doesn't even matter what's over here. We could just put on the other side of it what's storing into it. We could put the number 5, and that's just going to store 5 into anything. So 5 has now been assigned to anything. So we are going to store all this into there. That's what that stands for. We're going to call it GBM instead. For the train, does it have to be 60? No, it can be anything. I see a lot of times 50, 60, 70. Just depends on the size of the data. And then people like Dr. Seaver with larger data sets will take 5 holdouts. So he might take 50% train, 10, 10, 10, 10, 10. He might take 5 holdouts. Check out that. I think that was Wednesday last week where we talked about the theory behind it. It doesn't have to be 60%. There's no has to be in statistics. It's one of my favorite things. It's like, why does it have to be that way? It all depends, and you'll get different answers, and there's no right answer. All models are wrong. We're just trying to find a good one. So now we have to find our y variable of interest. So let's go right here and go to the train data. Let's try to predict how much somebody wants to weigh. Desired weight. Let's predict how much somebody wants to weigh. Now, what does the tilde dot mean? Tilde dot means what? And I purposely have an error in here if anyone catches the error. There's already one error. Tilde dot means what? All the x's. So we could go and do raised to second, or you could even go right here and do minus things like weight. We probably want weight. So that would subtract off the weight variable. We usually include all the x's unless otherwise stated, but this is all the x's. You can also take away x's over here if you did something like go to the row space and subtract out things like weight, or you could select them. But you could do it over there also where the data is being selected. We got our train data. Now, does anyone see the problem? There is a problem. There is a problem right there, right now. What is the problem? We don't have a grid yet. Good answer right there. We do not have a grid. That'll come up here in a moment. So we don't have a GBM grid. We'll make a GBM grid here, and we'll talk about that today a good bit. We don't have a GBM grid. That is true. And we can go ahead and grab the GBM grid right here. Here's the expand grid right here. That's just showing one. Let's go grab GLM net grid. There's a GLM net grid. K nearest neighbors. K nearest neighbors is such a good one. Should have done a K nearest neighbors. Might mention that a tiny bit today. There we go. Woo! Well, I like to grab this one. This is... Whew, you want to talk about power. Nick says, do you think you'll end up your office hours? You'll have to explain eigenvalues to me. I don't understand them and my lectures aren't helping. What are you taking with eigenvectors? Sounds like you're taking some maybe linear algebra or... well, we use them a little bit. So good to see your Snea. Oh my gosh, we got Snea and Nick here today. Nick, what are you taking with eigenvectors and eigenvalues? 533. Which one's 533? I have a question about the data under the link project. I don't know which one of the data sets I need to download. Can you show it? Well, it all depends which one you want to work with. Which one do you think about working with? Which one do you want to work with? As long as models in bio. 533 is one of the MSBA courses. Oh, wow, they're doing eigenvectors? Eigenvectors is basically dimension reduction. I saw there's a lot of data in link. Which one, though? Which one? There's multiple links. There's more links. We can talk about that here in a little bit. Or maybe message me on Discord to see which one you want to work with. You can also pick your own data set. Any data set you want. Just make sure you ask me about it. It's just some ideas to give you data sets to work with. You want to make sure you don't have a tiny little data set. You can get eigenvectors here in R if you want. But the idea of an eigenvector is dimension reduction of a multivariate system with multiple variables and bringing it down to its kind of principal components. That's how I use it, but they can be used a lot. So right here, we have the number of trees being boosted. These are the number of trees we're basically learning from. Interaction depth is how big we grow the tree. If it has an interaction depth of 1, so you know what's really cool? Stat to a 1, what does it look like? We talked about this last class. Stat to a 1, what does it look like I'm drawing right here? If I drew this right here, what does this look like? That's an interaction depth of 1. This is interaction depth of 2. That's an interaction depth of 3. And we basically have how many splits there are in the what? 1 interaction depth, 2 interaction depth, 3 interaction depth. Decision trees, yep. We're doing decision trees, but crazy powerful right here. We're doing like really crazy decision trees called gradient boosted models. It's like you grow a tree and then you chop it down and you grow another tree and you chop it down, you grow another tree and you chop it down, and you grow another tree. And we're either going to grow 200 trees or 500 trees. We're either going to grow them to an interaction depth of 1, 2, or 3, because this is a vector of numbers here. This is just a vector of 2 numbers. This is actually the sequence 1 through 3. And that's just how big we're going to go. Boy, does this... I know, right? Nice work. And then the shrinkage is the learning rate, how fast our trees will learn. Why do they call it shrinkage? I don't know. It's just the learning rate of the trees. Slower shrinkage is going to grow more trees that we give it options to, and faster shrinkage is going to have it learn a lot quicker. So it's just the learning rate. Number of min observations in a node is when you get down here to the very bottom, the minimum observations. Like, are we saying we're setting a rule such that you cannot have less than 2 observations? So that'd be we might overfit a little bit if we do that, but maybe overfitting's a good thing. It's never a good thing. We might make some really exact predictions, I should say, if we go down to 2, and maybe that's a good thing. Or we might only allow it down to 5 or 10. It all depends right there. And these are the values we're going to do right here. Now, here's a great question for the test. Good test practice right here. How many different models are there? You can cheat. But how many different models are being considered? Test question for 474. How many models are being considered here? How many models are being considered there? Good test question for 474. And the answer, you can cheat. So how many models are being considered there? I mean, you don't cheat on the test, but you can see the answer, and how would you know that? How many models are being considered here? I'll give you hints. Not 5. Good guess. Not 5. There's a hint. How many models are being considered here? This is when we talked about making cakes and how many different combinations of cakes. So you've got like 2 types of icing, 3 types of cake. Great job, Kirsten, right there. Yep, 36, and it's up there at the top. So these are the components you can make from, and you can make 36 combinations of these components. So there's all the combinations right there that we can put together of the number of trees, the interaction depths, the shrinkage, and the minimum nodes, minimum observations in a node. So all the combinations are over here. So this is when we go ahead and make this, it'll occur. Now, I don't know if anyone mentioned, we do still have a problem on here, and it has to deal with desired weight. One link shows that there is a test CSV and a train. You want to use the train, because the test, I think you're talking about maybe the census one. It doesn't have the answer, so you can't look at the target. You want to use the train. So we want to use the train. And if the test has, well, then if they give you a test too, and if they have a submit, so I'm trying to think of which one you're using. You want to make your model from the train. They might already have the train in the test for you, but you want to make your model from the train data. If they have the target on the test, you can fit it on the test. If they don't have the target on the test, you have to make your own test for yourself to see if your predictive modeling works. Good questions right there. You want to make your model from the train, and then if they don't have the ability to fit to the test, you want to make sure you can fit. So the test is holdout. If it has the target, if it has whatever you're trying to predict, you can use it as a holdout. Does that make sense? All exams are open tomorrow. All exams are open tomorrow. If the test has the target, you can do it. Does anyone notice the issue right here? So yes, with that data set, because I don't know which one you're working with from, I think there's 4 on the bottom. You're welcome. Good questions right there. Good questions. Does anyone notice the problem up here? I'm trying to point out a big problem. This is a huge problem. Desired weight's quantitative. Desired weight's quantitative. This is a pretty big problem we're going to run into. Pretty big problem. It's quantitative, and our fit control is categorical. So we should be able to just move this. We should. It's just assign, right? Method. Yeah. Allow parallel. Yeah. Sometimes we allow that. That allows parallel processing. Probably, and they have to do this. We probably need to allow parallel processing. I think it just speeds up the process. Let's just have to. Okay. So rarely used. Could not find function make cluster. I do not think we need to allow parallel processing. It's not the end of the world. It just makes things faster. Parallel processing. Maybe if we do something really crazy there, we'll put on some parallel processing. Okay, fit control right there should be correct. We got the cross validation. Number of folds is 5. We're not using the two-class summary. Not using the summary function. There we go. Do we have the right things? One thing you can do is you can double click your stuff to make sure it's the right thing. So if you see it highlight, you have named them the same. This is a real, since our eyes can really trick us. Does anyone else use this trick right here where you double click it, and if it's the same, it'll highlight? If there's a tiny bit off in the syntax where you have like a lowercase and uppercase, it will not highlight. So a good way to, I usually tell students, yeah, KP, it's a really good trick right there. There's an Among Us tier. Yeah. I love it, Shreya. How many points does it take to be evil Tiny Brian? I don't know. Good question right there. I can find out here in the in-between time. We'll try to find that out. I'm so glad people love the points. That means a lot to me. Nice little fun things here. Awesome. I think we're good to go. It's saying, do you have this package? You need to install GBM. Would you like to install it? Sure, why not? I reinstalled my R again this semester. It's installing GBM for me because it's going to leverage that in the train function. And so it's installing. Looks like it installed. Did it run my model? I think it did because we saw something up here. Yeah, it's over there. Okay. So now we can take a look at it. Now this grid is a little bit crazier. So there's the GBM, and if you note, it took a little bit longer than our models usually take to run. So let's go to plot and go to GBM. Woo! Here we go. Okay. Which one of these has the best right here? It's a toss-up. Should I go left or right for best right now? Now, which of these do you think is left or right is best? Which of these do you think is best, left or right? That kind of gives me some ideas. After taking 3... Well, Snail, I'll be back in class. I'll be back in person, not for, like, good. We want to go to the left because we're fitting for Armacy. So over here has the lower... Yeah, I know, right, Kirsten? You're like, wait, AUC, what are we doing? We're doing Armacy, so we want Armacy to be lower. So maybe that's 10, right? This one is going to be the best over here. And the colors of the line are min number of observations. But we get some good stuff over here. Let me redo this with the trees being, gosh, so many variables, right? It's crazy when you get this many. 500 trees didn't seem to be like a good idea. So we're going to do this right here. Now, by doing this, just tell me what I did to the number of models by looking at this. Just look at what happened right here with the number of models, because I went from 2 here to 4. So just think mathematically, 4 is doing this. So what happens to my number of models? And you can see it over here on my grid, right? When I click this and just look at that, you can see going from 2 to 4. And this is why just doing 2 more parameters here did what? Yeah, I know, right? Yeah, instead of Codehanger, right? Yeah, the one in my office on the Codehanger, yep. And we're going to be doing some Mario Kart, it looks like, at the start of the semester. So stay tuned. Hopefully we see lots of people get excited. It's going to be a lot of fun. Yep. Send the word out. I'll be back there in a week and a half. Oh my gosh. Craziness. Oh my gosh. Swing by. Say hey. We're going to have a big start to the semester. Do a lot of big things. We got a lot of stuff going on with the Business Analytics Society. I'm going to try to do a pizza party. I'm all about that pizza party. Got to talk. Oh, got twice as many models now. Twice as many models. Takes twice as long. This is where you have to watch out because it's going to take twice as long. your grid's going to be twice as big. Now we don't actually have to look through this. We can just look through. When am I moving? A year from now. 1 year. Gonna get some jobs in Knoxville for my wife. So over here, what we got? Wait, did it change where the trees are at? Where's my trees at? Oh, it's doing it this way? Wait. There's the shrinkage parameter. There's the min nodes per in what? Where's my trees? Well, that's the those are the trees down here. Those are the amount of trees. So the best model, look, 100 is winning. So 100's winning. So it's like less trees are better. Okay, let's try one more time here. Okay. Try one more time on this. I am all about tuning. Tune my piano, tune my trees. Shrinkage rate. Let's do a sequence from, what did we have previously? Let's do a sequence from 0.02 to 0.10 by 0.02. And let's throw another one in here. This will be, okay. This is our last run of this. If this was my job, I'd do even more because now our grid is 240. So it's going to take about, this is going to take probably about 4 or 5 times longer. No, it's going to take about 8 times longer. Where's the code you would use if it's categorical? Then you have to switch your fit control. Your fit control needs to be summary function equals, there it is right here. I use AUC, but does this make sense here that, where is it? Summary function, there it is. You want to use this one right here. If it's categorical, you need to use this one right here, Reagan. Oh no, Sneh, well, I'll be back. I'll be back hanging out and seeing everybody for a moment. Start a semester. Then I'll be back for good with my wife. So, woo! And let's see how the grid did. Crazy grid. I love these graphics. Okay. Okay, so here we are right here. We're really not getting much of a return. I mean, we're just bottoming out right around 10. So it's not like we're really finding something insane by doing the new grids, but you know, I'm going to always be examining. At this point, I wouldn't include a graphic like this. Even this is too much for me to understand. And if I'm having to take a good, like with all the variables right here, figuring out the best spot, and everything's bottoming out near 10 is what I'm seeing. So there's really not much of a return that we're getting. Let me go to the best model. There's the best tune right there, 150 trees, shrinkage, interaction depth of 2, shrinkage of 0.04, minimum observations in a node of 4. So there's our best tune right there. Let's go to the predict using the GBM. And so there's the predictions of people's desired weights. Let's go holdout. There's the predictions on the holdout. Let's go to the post resample. Here we'll go predictions on the holdout right here. Oh, we should have looked at, how did our GBM do? Our GBM did 9.5. We can predict someone's desired weight by, and we're typically off by about 9.5 pounds. So that's pretty decent. If you could, but I mean, like, I don't know, like, yeah, I guess you look at someone, you can predict their desired weight and you're generally off by about 10 pounds. Not so bad, right? Using all these variables right here, we're typically off predicting somebody's desired weight by about 10 pounds. Not bad. Not bad. Here's all our predictions on the new data. And now we put the predictions here, and then we put the actual values of the Y right here to check it and see how we did. I mean, little bit of overfitting Y. Little bit of overfitting, more than a little, I don't know. Oh, nice stuff, Isaac. When will the projects be ready? The grader said they'll be grading them today. The grader said they'll be grading them today. Vinish, I think you did a Brian company. I was reading through a few interesting projects. Oh. I read through some, but I didn't grade any. The grader, I have a grader for 201, or else it'd be craziness. I'm grading 474 and 475. So if you ever have any issues with the grading, let me know, though. Is this good or bad right here? This is where, now, once again, we read all the code, but then we need to know, so how do we find the ratio? And let's talk about what I would do with this right here. So what I would do with this probably is I'd probably create a data.frame, and I'd probably go in here to train RMSEs, or train dot RMSE equals, and let's go right here and go to concatenate vector. The train of it was this. You could store it elsewise, but we'll store it there. And then hold out dot RMSE. Oh, that's the, we reversed it. And then the train is, wait, yeah, that's right. Okay. And there we go right there. And now what I would do is I'd store this as results. And I would kind of be keeping up with this while I do it. And this would be GBM. And so now let's take a look at it. There's a little table. 475, conceptual exam is tomorrow, correct? Yep, conceptual exams all open tomorrow. So one thing we have right here, oh, Snag, good to see you. We're going to show a little trick here in a second, is let me show you a really great way to display results. So I took and I put my results into a table, which we could then do a ratio right here. I could go to results and store another variable and go ratio and store into ratio the results right here of this. We want to take the holdout top. And then divide it by the results like that. Okay, so there's the ratio. We stored it, and we're good to go. There's the ratio, and let's round this to 2 decimals. Okay, so now we have it. Okay, now I want to show you something really cool. A lot of people have been doing things like taking screenshots, which are not the end of the world. Schedule over there. A lot of people have been taking screenshots and grabbing code. Don't put code. People are going to say, we want to make this look really nice. You ready? We're going to make this look really nice right here. Even I got to remember, you ready? Let's do this. Let's go to library, cable extra. This is a package right here that uses tables. And I think we might be able to go to KBL. And let's drop it in right there, and it makes it into a table. Now that, you say, Brian, that doesn't look nearly as nice. But wait, there's more. And this is where we found out something really cool. Where is it? Cable. No. Oh, we might have to cheat and look at the package. Cable extra, here it is. You can do so much. We're going to make it look really nice. Cable, there it is. Okay, cable material. Okay. Cable. Much better, much better. I think we had a better one too. Cable, classic 2. There's a pretty good table right there. So all this right here could be input into your report. Much better way of displaying things. We could change the top names. Pretty good right there. And you could add your extra models. So if you get extra models right here, you could put the other values. We'll just put some fake numbers in. So they're not real numbers. But when you run this right here, you would add in your next model. We could say fake data. Don't put fake data in here. But you could take your results, and with just a little bit of work, you can get a table like this. This is going to look way better in report 474. What do you think of this right here? So how to interpret the ratio? You want the ratio to basically be 1 or less than 1. The better the ratio. Now, this means my error is 25% larger on the holdout. Does that make sense right there, KP? The ratio right here means my gradient boosted model had an error on the data it was created from of 9.5. I typically miss predicting someone's desired weight by 9.5 pounds. When I predict on the holdout, I typically miss, and this is the new data that the model's predicting on, I typically miss by 11.9 pounds. And my error on the holdout is 25% larger. That's the ratio of those numbers right there. So this right here, for mine, my holdout did better. It can. That can happen. That's not a bad thing. It's just what happens. There's not a bound right there. There's all these themes right here that you can use. That one does work. There it is. Yeah. So what do you think of these, KP, right here? Much better way of displaying things, I would say. You can put these into, you can export these. So you should be able to go to export to like a TIFF right here. If you really want, go to save image and let's export to, we can't export that as a TIFF? What? Well, that's a bummer. Let's say table of results. There we go. Yeah, it looks way cooler than the screenshot. So you're going to do way better if you just save your results right here as this, like this. And there's so many, this is just using the base cable package. So you just make a data frame and then you just run it cable and then you can pipe it into, this is called a pipe right here. But you're going to get way better and nicer looking results using this right here. Yeah, so you can make your results look however you want. And then just take this image right here. Like, let's do the following, and let's just see how this looks. Let's export, save image, and really? And then let's go cable, practice, and here it is right here. Let's go to copy. Let's go to a new Word document. Oof, it grabbed that extra. Now, if I got this, if this came in, you really want to go here and go to picture and go to crop. You need to crop that out. Don't leave that extra in there. And from here we have a pretty good table of our results. That's I would say it's not bad. Make sure to crop your images. But all in all, that's a pretty nice table of results. You could do a little tiny bit of flair, but think about how things look. Always, I wouldn't do that. I like to do the little. Oh, I wouldn't do that. Where's my one I do? Like the little. That's not bad right there. That's good, or that's good right there. I use that for PowerPoints mostly. You could do that. Just a little border around it. I'm just thinking about how much we've upped it. You're welcome. So I'll probably be telling people, especially today, you know, be thinking about how things look, because that is very important on how you present the things. You can also sort this table. We've put some fake data here, but you can list all your results. This is going to be much, much better than just a screenshot. So if you look, how hard does it look to be, KP, to make a table of your results? That's the longer part. I have a question about the exam. Is it multiple choice? That's for 474, right? There's multiple choice. There's numeric entry. It's a lot like the midterm. Good question right there. I just made fake data. That was just made up to like have more stuff right here, because you can just add like another model. So like you can add the values for another model. And so if you had more models, you could then get the results for more models right here. It's not going to lose the end of it, is it? Oof. Go to cable. This guy's so big. Cable. I don't know which one I like best. We could do some. That's like classic right there. Yeah, so you would just add them in here. And you see I just added in fake data. Like you would create this data frame right here. You could find the ratio of the numbers. Yeah, exactly. You want to present all your results nice and neat. So this is very important to 474. Like you want to display your results to people. Now, one thing we could do is we should be able to go to results, and let me see if I can use arrange and arrange by. There we go. So yeah, it did it good. So that code right there, and actually what you could do before you even do this, you could just pipe it in through this. Oh, it doesn't like that? Yeah, okay, I'm going to do it elsewhere then. Yeah, because you already have a cable. The cable doesn't let you arrange. That's a bummer. The cable is a graphic, I think, so it's not meant to be arranged. It's meant to be like formatted. So this arranges the rows by RMSE. It's sort of like order. That's how you do it with dplyr methods right there. Also there is a rubric called appendix. That's just like sources you've used, citing your work. Like probably give credit to like things you've used, packages you've used. Make sure if you look at how you don't need to go crazy on it. It's just to make sure you know that you're giving credit. You're doing an appendix right there, linking things like maybe the carrot package. Go grab links to that. I purposely put it in as a bonus just because I don't. It's important. I don't think a lot of business reports require it, but doing some citing, and that's just bonus. So it's 3 points, I believe. So I was like, sprinkle on those 3 points. Not that big. This is going to look like a super professional report. Oh my gosh, there's so much coffee grounds in here. Okay, I think there was a chi-squared question. Let's head over to the chi-squared. Let's do it. So really good questions right there. Good understanding of kind of, that's a more advanced model there, the gradient boosted model, and we looked through the different things that we can use for it. So check it out today in class as we do some gradient boosted models and also some forests. Woo, forest and gradient boosted models. I think that's where we're going to end talking about those models today in class and how to evaluate them. So a lot of fun coming up. Okay, it's time for a chi-squared test question. Okay, let's do this. Chi-squared test question 201, where you at? Chi-squared test examples. Here we go. Okay, when it comes to the chi-squared test of independence, what kind of data do we have when we do the chi-squared test of independence? Nice job. I know how to spell these things. There we go. Great job, Michelle, right there. Categorical X, categorical Y, two categorical variables. What is that condition called? The conditions for it are randomly select your data, 10%, less than 10% of your population is selected. We have something called expected cell count, less than 5. And the condition that you're speaking of, which is two categorical variables, is count data. So this means two categorical variables. The other ones are pretty self-explanatory. When we say that the expected cell counts are less than 5, that we have less than 10% of the population selected. UT is 30,000 students, don't sample more than 3,000. We randomly select the observations, so we don't just pick the first 1,000 people who come up and say, hey, I'd like to be in your survey. So when you think about what else we can talk about right here and do pretty easily, we can give you a grid. Now I want you to think about this question. Brian has 100 online students, very close to that right now, 100 Stats 1 students. Now, let's say 50% of students attend office hours. So this is attend yes and attend no. This is office hours. Do you attend office hours? So you're watching it right now, so you're a yes. And then we have on the final exam, let's say here 40 students make an A. Why not? Yeah, let's do 40. 40 students make an A and 60 students do not make an A on the final. I'd love it. This would be some great numbers. Now, without doing too much work, I don't want you to do too much work right here. You can see the two variables. I want you to tell me how many students who attend office hours would you expect to make an A? So here's your two variables, not A on the final, office hours yes, office hours no. So how many would you expect of the students who attend office hours to make an A? How many would you expect? That is correct. That is correct. So you can do the math right here, and let's look at the math. The math is going to be row total times column total over grand total. That is the math for an expected cell count. And so row total times column total, you multiply those together, and then you divide by the grand total right there. So 40 times 50 times 100%. So, or times 100, 40 times 50 times over 100. There we go, 20. But did you also think about it another way? If half of Brian's students go to office hours and half of Brian's students don't, and then 40 students make an A, you'd expect half of those students to be office hour students, right? If this is all due to randomness, then we should probably see if there's a 50-50 split between office hours, not office hours, 20 students here, 20 students here, 30 here. And do you know something really interesting? Once you know the answer to one of these, like if you know we expect 20 students here, it actually answers everything else. We'll talk more about that here in a second. But let's say we actually see, this is the observed amount, we actually see 35 students here. That's the count. Does that make sense what I'm saying when I say we actually see this? Who understands what that means? If I say we actually see 35 students, like do all the numbers on the screen make sense? We actually see 35 students who attend office hours making an A. We actually see that. That's what happens. We expected 20 by random chance. Like if there's no relationship, we should see 20. That's what's the most expected. Not like we will, but that's the most expected thing if there's no relationship between office hours and making an A. But we actually observe, that is the observed amount. We observe 35. Who understands what the 35 right there means in the table? That we observe 35 students who attend office hours making an A. There might be, and it looks like that, Jessica. It does look like that right now. Well, we don't know that there is a relationship yet because we haven't ran the test, but it looks like there is. Does that make sense? It would seem just by people who, if we don't even use statistics, it seems like there is, because that's pretty far off from what we expect, right? More on the chi-squared here in a second because we'll calculate it for this. So, but does that 35 make sense to say there were 35 students who attended office hours and made an A? There were 35 of the 40 who made A's, of the 35 who attend office hours. So what number would go right here for the students who do not attend office hours who made an A? So what, and this is an A on the final, just an A on the final. And that's the observed, correct. We observed 35. We observed 5 students. Now, these are not the expected. This is just what we saw. We saw 5 students who do not attend office hours making an A. Notice how these add up right here to 40 right there because they're the observed. And now down here, how many students did not attend office hours who did not make an A? Okay, good. Yeah, Michelle's seen it. Great job, Michelle, right there. How many students did not attend office hours who did not make an A? So they did not attend office hours and they did not make an A. How many students would that be? I'm talking about this one right here. Not attend office hours, not A. Not attend, not A. 40, yeah, exactly. 45, right? You know what's interesting? Do you know why you can solve all these numbers right here? Is there something about this table? And if you were to remove one row and one column, is there something about this table, mathematically speaking, where if you said this is a 2 by 2, and what do you notice about a 2 by 2? A 2 by 2 has how many degrees of freedom, which is rather interesting because as soon as we know one of the numbers, we can solve all the other ones, which kind of makes sense why it's called degrees of freedom. It has 1 degree of freedom, right? So because there's 1 degree of freedom, which means there's one value kind of that everything else is contingent on. If you know one value in this table, every other value has to be solved, which we just did. We said, okay, there's 35 here. Everything else was a forced choice. There's 1 degree of freedom. We don't really use it that way, but it's a good way to kind of even see like, oh, there's 1 degree of freedom in this chi-squared test. So once we said 35, everything else was a forced choice. So actually by knowing that there's 20 expected here, you can solve out all the other expecteds because they're all forced choices. So now that we have the observed and we have the expected, here we'll highlight them with the colors of what they are. The observed is going to be all the large numbers right there. There's the observed. And then the expecteds are all the greens. So the expecteds right here. 2 seconds. And so now we need to calculate the what's right now. Now we need to calculate the what's. What is this formula right here? That formula over there is what we're going to be doing on the side. So we need to calculate all the what's. And technically, these are these. Observed minus expected squared over expected. Every one of these. The cell chi-squareds. Great job right there, Meath. The cell chi-squareds. So think about, you know what's really cool about this? They all have a difference of 15. Positive or negative doesn't matter because we'll be squaring it. So let's do the first one. Are you ready? The first one right here is going to be observed of 35 minus expected of 20. Now we're just doing the observed minus expected, difference of 15, square it, divide by the expected, which is 20. That's 11.25. So 11.25 is the cell chi-squared. It would also be here. And then the bottom ones should be 7.5. And so with this, and double check your math, see if you can solve it, what do we do to all these cell chi-squareds now? With all the cell chi-squareds that we calculated, we do what with them? With all the cell chi-squareds, talking to Mubot in the chat, what do we do to all the cell chi-squareds? What do we do to all the cell chi-squareds? This is a review from last night. So now that we have all the cell chi-squareds, what do? We sum them up. So we sum them all up, and that should be 15, 22.5. So that's 37.5. Correct me if I'm wrong, 37.5. So 37.5. No, it's 30? It is. No, wait a minute. 11.25. 11.25 plus 11.25 plus 7.5 is 37.5. I saw it, but I clicked wrong. 7.5 plus 7.5 plus 11.25 plus 11.25. 37.5. No, 37.5. Great job, Michelle. Oh, did I say it wrong the first time, Michelle? I think I might have. It is 37.5. How do you know that the cell squares from observed 5 is also... Are you talking about with the 5 one right here? So here we'll check it. It's 5 minus 20, which is negative 15, but we're squaring it. So it's 225. 5 minus 20 is negative 15. Square it. Thank you, Michelle. And then we divide by here 20, and we double check it. Because the expected was still the same, and the difference being positive or negative is not going to matter since we squared. Does that make sense, Meath, how I thought through it? The difference is the same, and positive or negative won't matter because we're going to square it. So since we're squaring the difference right here, this is 15 difference, this is 15. A lot of times when I do it, I just look at the difference because we're squaring it. So I just say, okay, that's 15 away, that's 15 away. The positive or negative won't matter. What does matter though is what we're standardizing by. If you notice, the expected is the same here, and the expecteds are the same here. That's why this one's different, because it has a different expected value it's being standardized. It's still a difference of 15. And then just check your mathematics to see if you can solve and get these. Yep, and expected is the same. Yep, so you're seeing it. Good practice. Now that we have this, we need to go to a chi-squared app. And the p-value is going to be 0. You'll see here in a second when we put this in. Degrees of freedom 1, we're off the curve. We found a chi-squared of 37.5. So the p-value, this is on the equation sheet. Good question right here. The equation sheet is going to have all of these equations that we've been using. And you'll notice here at the chi-squared test statistic, we found a chi-squared of 37.5. The p-value is 0, which means this is extremely strong evidence that we see a relationship between attending office hours and making an A on the test. So the formula sheet has these at the bottom right here. These are the formulas we've been doing right here, where we talked about the degrees of freedom, rows minus 1 times columns minus 1. The expected was row total times column total over grand total. Grand total is n. The sum of the cell chi-squareds, this is a cell chi-squared right there, is the chi-squared test statistic. And all of this was reviewed right here on the following question. We did a lot of the work right here. Any questions? This was a pretty big example going through a full chi-squared test. And we would say we reject the null hypothesis that making an A is independent of going to office hours, because the p-value is basically 0, which is less than 0.05. We have evidence to the alternative that attending office hours is associated or not independent of making an A on the final. Any other questions? Really good chi-squared practice. Let me see. Head over here to the main screen. It's open forum for questions. Open forum. Awesome. I have a meeting with a student here in 15 minutes. 15 minutes. My Pearson is messaging me. Who is got like a new My Pearson rep or something? Awesome. And set up an alumni panel, all this great stuff. Does the 16 F-15 attendance? I think we have it for. Do we have it for 75 also? I should have done it for all of them. I think I did it for all of them. I think so. I'm gonna drink my coffee grounds. Good coffee grounds. Best coffee grounds ever. You know, we got a really cool Ninja coffee maker. It's really cool because it puts so much coffee grounds in my coffee. Yeah. It applies. Here we go. Show you real quick. Woo! So the test closes tomorrow at 3. No, the test is open all day tomorrow, right? This is 2:01, right, Jessica? Why was the p-value 0? I'll show that again. Attendance does have, this is 475 and 474. Should be for both of them. It says weekly quizzes, but we do not have quizzes. Oh, that should have been gone. Weekly quizzes. There are no weekly quizzes right now. Those, I think I must have left in something. No, there's no weekly quizzes. No weekly quizzes. So Jessica, it should stay open all day tomorrow. Does it say the test? So the test closes. It closes at 3:30. Let's fix that. Why did it close at 3:30? Yeah, it does. Why did I do that? I'm trying to think. Why did I do that? Yeah, no, let's fix that. Well, thank you, Jessica. Jessica, 1,000 points. Why did I set that up like that? I'm like trying to remember my reasoning and being like, oh yeah, we need to do that. Huh. Well, I'll be. Wait. Oh, it's opening today? I don't know what I do. I don't know. I don't know what I'm doing. It's opening here in a little bit. I need to do, since it's opening, I don't want to change anything. Someone might have already, okay, so now it should be opening the whole time. Maybe you moved it when Pearson was, no, I shouldn't have, because I wouldn't move it, I wouldn't change, maybe I did, maybe I somehow was, man. When, I need to make some changes here while we're talking then to make sure people have what they need. Maybe, yeah, like when my Pearson was down, I was so frantic. Like that threw me for a loop. That was like a whole weekend of me trying to figure out how to handle everything. You know, we added some additional drops. I hope that, did everyone feel like that was fair? Like the best thing I can do when everything goes crazy is try to fix it and help people out. So, you know, it's really tough. It's really tough to be like, how are we awesome? Thank you so much, because I always want people to tell me like, hey, I don't think this is fair. Like, it's just tough because you never know what's going to happen during a semester. Like, hey, we lose my Pearson for like 3 days and then people can't do their work. So that's, you know, really tough. Getting things fixed up here. I want to make sure everything's right for the exam for everybody. Okay, good. Oh, Brian, past Brian, you already did the work? Double checking. Making sure everything, yeah. Looks like past Brian already did his work. Whew, I tell you. Yeah, okay, past Brian. Thank you, past Brian. You did your work. Wow. Past Brian did what past Brian was supposed to do. Some days I sit down like and just get a whole bunch of things done, and apparently then I don't. So I don't put it there on my checklist. I got a checklist of things. It's a good way to keep track of stuff. But I'm a checker. I got to make sure I see it and that it's done. So now it's open all day tomorrow. Yep, open all day tomorrow. Evil Tiny Brian messed up the data. Man, Evil Tiny Brian. He's just... He's even got the lamp over there. He's got the... You can't see it. That's my... it's the key light right there. So it's kind of interesting. This is why sometimes after long streams, I get pretty drained. There's actually bright lights on me. Bright lights! Ah! We just mess with my green screen lights. How do you do that? There's lights everywhere in here. Lights, bright lights. You're welcome, Jessica. Thank you for saying that. For the Force Entry project, if we have a category variable, are we allowed to look at accuracy? I mean, you can. Yeah, Gustavo, you can. I prefer AUC. I mean, I can't, you know, explain to the reader why you're using accuracy. Talk to them why it's important. I prefer you need to know what AUC is and how it's calculated. I prefer AUC, but I'm not gonna take down someone's take the grade lower because of it. As long as you know, display it and show it. We talked about checkout earlier in the stream. We talked about how to display stuff really well for the project, because we are looking for you don't want to just be screenshotting output. You want to be making really nice tables, and we talked about that earlier. we went and made this table right here. Let's put this section in here. Reminder, make really nice tables. 474 reminder. So this goes to reminder for 474. BAS 474 reminder, make nice tables. Okay, so this table looks like it's a bunch of high effort, like we're gonna have to write a ton of code, but in truth, as long as you have your data created and created nicely, not that much work. Not that much work to create the table. I'm using a package called Cable Extra right here. And so library Cable Extra. I've got the results right here stored just into a data frame. So that's literally just a data frame of results. Is lab 8 our last lab? It is. I'm using the applet to find the p-value for the chi-squared test. Would the p-value be given, or will we need to find a bind? Oh yeah, Michelle. Yes, you would not be using, like you might have to look at pictures on the test, but we usually don't have much with like solving. You won't have to use applet type stuff. So great questions, Michelle. And there was a question about the chi-squared. Did everyone get their questions answered? We're going into office hours a ton bit early today, because I got a meeting with student. And so, and it's a lot going on. I'm excited. I can't believe it. Last 2 days of classes. Exam is now open all day tomorrow. Good stuff right there. Probably scared some people because exam was. I asked you how you knew the PO is. Oh yeah. Okay. So, the reason the p-value is 0 is because when we do the chi-square test of independence, we need to first put in our what. Before we use the chi-squared applet, we always put in our what. Like if we're using the t or the chi-squared, we always put in our what first because we have to know which chi-squared or which t we're using. We always start on these applets by putting in our what to start, which tells us which of the t's or chi-squareds we're using. So before you enter in anything, you always say, okay, wait, I'm doing a t with this or a chi-squared with this. Now we're doing chi-squared, so we have to know the what for our chi-squared. So we have to always know for our chi-squared, we have to know its what's. Before we enter in, well, we'll enter in something in here, but we won't enter in the chi-squared value yet. So whenever we do the chi-squared or t, chi-squareds and t's always have with them degrees of freedom. Yep. So this is a 2 by 2. There's 2 answers here, and there's 2 answers here. It's a 2 by 2. So how many degrees of freedom are there? Since this is a yes, no, 2 answers. A, not A, there's 1 degree of freedom. 2 by 2, 1 minus 1, or 2 minus 1, 2 minus 1, it's 1. And so there's 1 degree of freedom. So we go to 1 degree of freedom. Now this controls the shape of the chi-squared. The chi-squared with 1 degrees of freedom is the most skewed. The more degrees of freedom the chi-squared gets, it's kind of like the t, it gets more normal, but also the degrees of freedom are the center. You don't have to know the complexity at that level, but notice how the center of this curve is 111 and it looks more normal. The chi-squared becomes more normal as it gets more degrees of freedom, and you really need a lot, I think around 30 till you can get a normal approximation. Once again, look, 30 is the center of the chi-squared, but you don't need to know it that in depth. This is why I was able to figure out that there was probably a p-value of 0. Since I know it's extremely skewed, I also know that the chi-squared barely goes up to about 10. And these, like, it keeps going, but beyond 10, there's basically what amount of area? Like over here, there's almost, and I put 9 so we could actually see it, above 9, there's basically what? Now, I know that's not it, but there's basically how much area above 9 on the chi-squared with 1 degree of freedom. The chi-squared with 1 degree of freedom, we basically have how much area above 9? We basically have 0. So think we're even further over. We're off the screen over here, right? We're over, way over here off the screen. So we're over here at 37.5, which it doesn't even show us because it's so far off the screen. So at 37.5, now we get a p-value of 0, it says right here. Now what's really cool and why I love all the things we can do, we can actually go right here. I think it's Q, is it p chi-squared? So 1, and that should be 2. There we go. That's the area below it. There's the area above it. 15.7. There it is right there. So we could actually try to calculate it. It's probably gonna, there it is. Here is, there's the p-value. So if you're wondering what the p-value is, There is the p-value for the test, 0.0000000000009. But we have to use something a little bit better to calculate it, Michelle. Does that make sense? It's so far off the curve that there's that little of an area. So that is the exact p-value. And to calculate it, we're going to do something a little more complex than using applet because it's such a small value. I had to turn my scientific notation. I could have used the scientific notation for it, but I was like seeing it. And then I turned the digits on to get more digits. But there's the p-value right there. And for all intents and purposes, yeah, Michelle, hopefully that helps. This is just a more advanced way of calculating it. The p chi-squared does the area to the left of it. So I did 1 minus. 475 Kahoot during class. What? Yep, during class time. Great job, Thomas, right there. Kahoots. We'll probably do I think I've got a 474 Kahoot. Is there a lot of calculation things by hand for the test? I mean, some. There's some calculation by hand. Like we did a few of those over here. We did them right here. We did some by hand calculations. So these are the calculations you'd kind of expect to do by hand. These ones right here are ones I would kind of expect to do by hand. Awesome. Well, with that, I have a meeting. We'll be back here tomorrow. We'll be doing some Kahoots. Woo! We're gonna get some more coffee. We're gonna drink some more coffee. Look at it. Look at those all those coffee grounds. My God, Ninja Coffee Maker, best coffee maker ever. Great job, Michelle. Great job, Jessica. Let me know if there's questions. Kayla, so good to see her. How you doing, Kayla? I'm gonna be in town. By gosh, I'll be in town in 9 days. Holy mackerel! I got to get that Uber booked to get driving down to the airport. I'm gonna fly into Knoxville, see everybody, say hey. We're gonna have some Mario Kart tournaments, I believe. I think we got everything booked. Got to get a hold of Mark Willoughby. It's gonna be so much fun and so excited to see everybody. Oh, you start law school? Yes, Kayla. I should walk down to law school and say hey, and that'd be really cool. Like, yes, Kayla, congratulations. And I just want to say this. This is my last word on this. Everyone here knows I love statistics. Oh, swing by has some college of business. Be like, where's Brian at? Everyone knows that Brian loves business analytics, but you don't have to love business analytics. I am so proud of you, Kayla. I'm so proud of so many of my students. I love seeing students go into the MSBA program, but I want to say this, Kayla, I'm so excited that you're in law school. That is so cool. Law school was actually one of my dreams for a little while, so maybe there's not like jealousy, but I'm just like, oh, that's so cool. Like, my cousin Mark's a lawyer, and like I look up to my cousin Mark, so I don't know. That's really cool. I think being a lawyer would be a fun career in some ways. And so I'm really excited for you. And it's not just that I get excited when my students do things that I'd be excited about, but I know you were super excited. I know you're super happy about it. And I just want everyone to know that you don't have to do business analytics. I love business analytics. Come on. That's what I do. And if you're excited about it, my 2-year-old daughter just got excited. Oh, well, you know what? This goes out to your 2-year-old daughter. You know what's going to happen here. You ready? Check it out. We're going to try not to get a copyright claim. Bye for now, everyone. Bye.